This is a series of 10 lectures on foundations of physical law. And this one is going to be a gentle introduction. There's nothing technical in this lecture, it's about methodology. But I think it's absolutely essential that we get this right before we get onto the more technical issues. Because this is why we can do something different if we get a different methodology for it. So, if we're looking at this subject, we find that there are a lot of difficulties with it. It's rather risky to do this at all, because the subject doesn't really have any status within physics at the moment. There's no obvious career, structural, or financial support. Impact, of course, is negligible. No prizes. There's not even any journals, really. There's a journal called Foundations of Physics, but it's not really about this. It's about other things. And this is the most important of all. There's no protocols. There's no structure that's accepted from which you can start to work. And there are many people who think the subject shouldn't exist, or they behave as though it shouldn't exist. So why should we do it at all, given all the problems? Well, because it really is as cutting edge as you can get. And this is why it's difficult to do, because there's no systems in place and it's not yet integrated into physics. But that's what I would like to do with it. I'd like to integrate it into physics, make it a significant component of the subject. The problem with it is that in physics we're always trying to push back to the origin from something more complicated. We start with a complicated world around us and we try to push back, project back and get to what might possibly be some sort of initial conditions, initial beginning of some sort. And so we haven't got any basis on which we can start, because we're trying to find the basis. So we've got nothing from which we can start. So until we actually reach something more final, then we've got no basis, because the final is the starting point, and that's why it's difficult. And as we know, scientific method is mostly structured in the opposite direction. We've got starting points, for example, we have Maxwell's equations or quantum mechanics, and we start by building and explaining various things using it. But we can't do in this case. We've got to try and work the other way. So it's intrinsically difficult. Yet, even though it's difficult, we should persist. And this is one of the reasons why we should persist. We've got the standard model of particle physics, a wonderful theory, brilliant, magnificently successful. Too successful for many people, because it seems to be, the experiments seem to keep reproducing the standard model's results and saying how good they are. And many people would like something to change. But it is only a model. It's never been a standard theory. It's not a theory. There's no structure which explains it. It is a set of facts gathered into a structure, but it's not a fundamental structure. It doesn't start from some other place and explain why we get to the standard model. We've had this standard model since 1973. We've had no really major advance on explaining it in 40 years. So we've got to try to get to it from some other route, or get to something from some other route. Now, what many people think we should do is a kind of combination. They say we should take quantum mechanics, we should take general relativity, the two most accepted theories we have, put them together somehow and make a bigger structure involving both. And I don't doubt that we should do that. I don't think that's the only thing we should do. There's something else we need to do. We need to ask other questions other than the questions that we would get by putting those together. If we truly want to reconcile them, we have to find foundations on which they are structured. Where do they come from? Because even if we were able to put them together successfully, which we haven't managed to do, we've still got to explain where they come from. There's still huge unexplained things within them. So, if we're looking at this subject, it isn't particle physics, it isn't general relativity, it's not quantum mechanics, and it's not any kind of extension or combination of them. It is a search for the explanations of such theories and everything that can explain them in different ways. So we're looking for the common origins of physical theories, their common origin with mathematics, and that's another big question we want to look at. We want to know about the, as Wigner said, Eugene Wigner said, the unreasonable effectiveness of mathematics in physics. Why do we use mathematics? Why is it so effective? And there's another side to that, because nowadays there's the unreasonable effectiveness of physics in mathematics, which is the reverse side of that. Because lots of mathematics is being produced only because of the physics that drives it. Now, if we were able to do that, if we were able to get at this level and get somewhere with it, make some headroad into it, then we would be able to explain many things in other areas of physics, certainly in classical physics, relativity, quantum mechanics, particle physics, maybe even other areas of science of greater complexity. Maybe we could extend to chemistry or biology, or quantum, or computing science. But I say this is like finding the technological consequences of blue skies research. Wonderful if we do. Everybody is really pleased if we get a technological consequence of some blue skies research. We know that it always happens. And we're very happy to see it happen, but we know that's not why we're doing it. We're doing it because we want to find the answers to the blue skies questions. And again, we want to answer these foundational questions, so again we want to make headroads into these subjects as well, but that's not why we're doing it. So I'm going to say this is a separate discipline within physics, and that's the way we've got to look at it, that we're doing something different to what we've previously done. We've got to take on board all that we've previously done. We've got to accept all the physics we already accept. We've got to build that into our structure, but we've got to do something else as well. So we're not trying to replace anything we've got, we're trying to do something in addition to what we've got. And we will need all that as well. So we've got to do a completely separate way of thinking and methodology. It's obvious that we have, because we haven't made any headroads, so we've got to find another way of doing it. And I don't deny it's intrinsically difficult, and there's no formal description within the scientific method we can yet use for it. But it doesn't mean it can't be done. There is a thing that scientists have always used, and this is induction. So we infer a cause from given consequences. Now, we've obviously got to use induction because that's what we're trying to do. We're trying to infer the cause from consequences. But when we're studying this area, we've actually got to take the induction to a much more extreme level than we normally do. We've got to use a lot more induction. And this is because the causes are more general than the ones we usually investigate. So we've got to be more imaginative. We've got to be more wide-ranging. So our training tells us to deduce certain consequences from what we have, and then sometimes to induce something from them and push back a little. Carefully limited induction. Well, we've got to be a little less limited when we do this kind of induction. We've got to think outside the box more than we would normally do. The box being physics, as we've been taught to understand it. Not that we have got any objection to that. No, we haven't. That's great, fantastic. But we've got to find something which is additional to it. And at first sight, it may look different. And it ought to be simpler, because that's the way nature always works, from simplicity to complexity, not the other way. But it ought to eventually automatically give us the familiar structure when we make the right connections. So that's what we've got to do. We've got to get something that looks different from what we've normally done, but that will give us what we've normally done and lead to it. So that's the only way we could possibly make progress in this area. Now, it's clear that we can't just randomly speculate. It's no use at all. Completely pointless. That won't get us anywhere. What we need is to actually say, what protocols are we going to use? What kind of structure are we going to start from? And I say we actually need a theory of knowledge that's even more fundamental than the knowledge we want to generate. So our theory of knowledge has got to lead to the new knowledge. It's not, if we don't have the right theory of knowledge, we won't get anywhere. It's a philosophy, if you like, and a metaphysics in the sense that it's a subject that talks about physics, which is what meta of anything means, but perhaps it might even need to be a metaphysics in the usual sense of that word. Now, it is a philosophy, but it's not philosophy as usually talked about. We're not talking about the nature of quantum mechanics in the ordinary sense. We're not talking about whether there's a God or not. We're not talking about philosophy of physics either, the sort that talks about Schrödinger's cat and such things. We're not talking about that kind of thing. We're not talking about philosophy of science. Philosophy of science is the sort of subject which says how does science operate. Those are all interesting subjects, but that's not what we're doing. What we're doing is philosophy of knowledge. We have to have a philosophy of knowledge. And we have to have one strictly geared to our specific purpose of looking at the foundations of physical law. And this is not, there's no point in coming out with generalizations and that kind of thing. We've got to be very focused in what we're doing. It's got to be highly technical. We've got to find those more fundamental principles of knowledge which will help us to choose fundamental principles for physics. And then say, yes, that's the kind of thing we want. We can recognise them. That's what we've got to do. We've got to find some way of doing that. There's no hope whatsoever of saying, well, I'm going to sit down and design such a philosophy of knowledge. You couldn't possibly do that. No one's ever been able to do that. The only thing you can do is do a symbiotic process. You look at physics, and then you do a little bit of that, and then you look at physics again and do a bit more of that. And it's got to be a symbiotic feedback, positive feedback mechanism to keep developing one with the other. Then, and only then, can we start codifying the principles for use in other cases. Right. Now, this is the sort of thing that I've been involved with for quite a long time, so I'm going to tell you, what I've managed to develop in this area, so that we can see if that would lead to anything of interest. And the first question I'm going to ask is, how is it that we can develop a picture of the world which is completely different from the way that as physicists we know it is? Because our picture of the world is based on something that's 15 orders of magnitude bigger than the proton. And the proton itself is a complex structure. So how did we manage to do that? Our environment is completely different from the environment at the fundamental level of physics. So how can we actually understand it at all? So there are things that are complex, which are very familiar to us, but don't actually help us to do that. So how can we do it? Well, there's only one capacity that we have that can do that. There's only one talent that we really have. Complexity leads to emergent properties not seen at a less complex level. And a classic one is solidity. Oh, solid table this. Solid matter. Everybody thinks that's solid matter in the normal way of thinking. But of course we know it isn't. We know that it's all about points, interacting points. Point particles. There's no solidity whatsoever. Solidity is an emergent property. That for centuries we thought that was one of the most certain things that we knew about solidity, but it isn't in fact anything more than an emergent property. It's not a fundamental one. Of course, explaining how we get that emergent property is an interesting thing in itself, but it's not what we're looking for. So we've been deceived. It seems to us normal to consider solidity, but we have been deceived. And in fact, there's a famous story by the 18th century writer Samuel Johnson, who somebody said, what do you think about the philosophy of Berkeley, that everything is all abstract and so forth? And he kicks a stone and said, thus I refute Berkeley, because a stone is a solid object. So that is the common sense view, is that stone is solid, but we know that it isn't. There's no such thing as solid matter and substance. So it's only an emergent property, and there's no such thing as an extended object. As far as we know, there are only points. So material objects, so-called, are just an interacting point, an otherwise empty space. So we've got to find out what is how we can get around this. So how did we manage to develop our view that we've got points in interacting space and not something solid? How did we get there? Well, we got there because we used the one talent we have, which is pattern recognition. We had to have pattern recognition to survive in earlier states of human existence. We'd not have survived without recognizing predators and other patterns that they needed to recognize to survive. So we've evolved to be able to recognize patterns, and of course not just us but other species as well. Now interestingly, nature seems to reuse the same patterns at different levels of complexity. It's a kind of self-similarity. Perhaps it's related to a fractal concept, but there is a sort of self-similarity in nature where the same sort of pattern emerges at different levels. And we can use patterns we've learnt at our level down at lower levels, and that's worked very well. And so also we can also recognize when the pattern doesn't recur. So that's two aspects to pattern recognition. We've got, yes, that's an existing pattern. Oh yes, that breaks the pattern. That's not the same. And we're good at doing both of those things. Now mathematics is a classic example of self-similarity. So we can use the same mathematics at many levels. And that's a recurring pattern that we can use all the time. That's the classic example of it. And naturally, pattern recognition is one of the key aspects of thinking outside the box. You recognize a pattern, you say, I've seen that before, or that looks like such and such, and you can bring your knowledge in one area to bear in another. Now, clearly mathematical structures are at the heart of physics. Without mathematics, we wouldn't have the physics we have. We know that it must be mathematical. But somehow there must be a transition from relative simplicity at foundational level to more highly developed levels, to more complex structures at higher developed levels. And we must see how that happens. We must try to observe that transition and get there. A highly complex, this is very important in my view, a highly complex mathematical model can't be a foundational one. It can be brilliantly successful at explaining many things, but it isn't foundational. I hate to mention Ptolemy's epicycles, but Ptolemy's epicycles were brilliantly successful doing what they did. And no one will deny that. For centuries they were the classic way of working out where planets and were and so forth. But they're not the real answer, they're not the foundational answer. So that's very clever, brilliant mathematics, but it's not the foundational answer. Somehow nature isn't clever in that way at the foundational level. Our cleverness and nature's are different. So we mustn't assume that nature follows our cleverness. We must try to find out what nature's cleverness is. And it's different. So we must find some way, if we use simpler, so-called, they might not actually be simple at all, but with simpler mathematical structures, must have a natural progression to the more complex ones we use that we're already familiar with. So we've got to find mathematical structures that are simple, but that lead to the more complex ones that we're going to use at a later stage. Now, people often say mathematics is a tool used in physics, and I would dispute that utterly, because it is a tool used in physics, but it isn't just that. It's built into the structure intimately. They're totally connected at the basis level that you can't separate them. There's something about mathematics which is essential to physics and vice versa. They're not separate subjects, they're part of the same thing. And it isn't just that, oh, it happens to be convenient. People often say mathematical equations are convenient, but they're not. The ones we use in physics aren't convenient at all. They're very inconvenient because we often use differential equations, of which there's no obvious solution. It's not a simple solution. You have to then stick in initial conditions and all kinds of things to actually get any kind of approximate solution out of them. So that isn't convenient. We're not doing it because it's convenient. We're doing it because it's the correct structure to use. So the mathematics must be deeply built into the structures physics needs for its foundations. And always the progression should be from simplicity at low levels to complexity at high levels, never the other way. So if we come up with a complex, brilliant equation, then I don't think that's going to be foundational. It could be fantastically useful, but it won't be foundational. It won't look like that at all. So I don't think explaining complex systems using complex mathematics will actually help us to understand foundations. However, there is something that will help us that we have become much more familiar with over recent years, certainly in the last century. So one particularly significant type of pattern has become of immense significance. And this is giving us a very strong indication of how mathematics can start from something simple, seemingly anyway, and lead to something which is obviously complex. And this is symmetry. And it's all about us in the laws of physics everywhere. There's all kinds of symmetries. So symmetry is absolutely fundamental to physics. We see it in the fundamental interactions, fundamental particles. We see it in other areas. We see it in biology. We see it everywhere. Symmetry is clearly a key to this. If we get a symmetry, we can help to decomplexify our explanations. And we might get a more profound understanding than we would if we had a complex explanation. We also know that some symmetries are broken. And this is really quite a big clue to us, that some symmetries are broken. We believe that under certain conditions, that what would look like a perfect symmetry no longer does so. And that does give us a clue, because that tells us how things are complexifying. That leads us on to how we can get to complexity from simplicity. The reason can't be arbitrary. You can't nature just happens to have a broken symmetry. That couldn't possibly be true. Nature doesn't do that kind of thing. If it has symmetry, it has proper symmetry. The broken symmetry comes from some other thing. If we have a broken symmetry, then that will not be fundamental. We know that if it's broken, it's not at a fundamental level. Nature would never act in such an arbitrary way. It is a sign of complexity or emergence. And if we can find the source of that breaking, then we can work out how that complexity has come from the simplicity. So that's a fantastic clue if we've got a broken symmetry. It's a really helpful clue. And avoiding the arbitrary is going to be a cardinal principle. And by this I mean is that if you believe in physics, you can't say, well, physics works up to this point and then we stop using it. You know that you can't do that. If you go for physics, you've got to go for it forever, all the way. There's no point at which it stops working. You can't have explanations at which point physics ends. Can't be done. No such thing. It has to be the total and final explanation. It has to be physics, ultimately. And it has to be true without exception when you get to that level. If you believe in its unqualified truth, that gives you a strong thing that you can use for regulating your theorizing. You believe in its unqualified truth. And that's why physics is so powerful, because we believe in its unique strength, its unqualified truth as an explanation of the universe. There isn't another explanation, there's only physics. We may not have got to that physics, but we know that it has to be like that. There can't be anything else. I'm going to say at this level, what I have found from my own experience is that if we decide we've got a correct direction, we have to go for it. We haven't got to compromise. We've got to go for it ultimately. Say, I'm going to push down that direction. My hunch is that it's there, and go for it. Utterly ruthless in pushing it to its limits. For example, and this is a very important point, physics in its foundations has to be totally abstract. And this is what quantum mechanics will tell us. There's no sort of material bit and an abstract bit, there's only an abstract bit. There isn't both. So there aren't tangible objects and purely abstract concepts. Space and time, like space and time, you can't have both. It's like having gods and humans in a story. It can't work. You can only have one thing or the other. It's illogical to have two different types of explanation together if at a foundational level. So we have to go for the abstract. Everything must be. I was mentioning about point-like particles before, and the evidence that we got from experimental results on point-like particles suggests that the true reality is the abstraction. There isn't anything more real than that. That's all there is. There's only abstraction. In a way, it's mathematics. There's nothing else. Tangibility is only an emergent property at high-level complexity. There isn't anything real or tangible. It's just pure abstraction. And only this abstraction will bring about the link with mathematics that we desire. If we don't do that, we can't 100% link with mathematics like we need to. Now, what I'm going to say is that quantum mechanics is not a calculating device. People talk about I don't like quantum mechanics because it doesn't give me the world I'm familiar with. It gives me this set of equations which I can calculate. That's great, I can get my calculations right. That to me is no good. We've got to accept quantum mechanics for what it is. Quantum mechanics is real explanation. It's not a calculating device only, it is more than that. It's an exact indication of the way physics should go. It's giving us the clue. Instead of saying quantum mechanics is a problem, as many people do, we should say, no, hell, that's giving us the opportunity. That's what it should be like. It should be strange like that. It should be abstract. That's giving us the clue where we've got to go. It's not only what physics is like, it's what it should be like. It ought to be like that. It ought to have that kind of strangeness. We need to look for something that is really simple, yet can generate complexity. If we start with, say for example, as a string theorist would, 10-dimensional structure. I'm not saying you can't get anything out of that. You certainly can. You can get plenty out of that kind of thing, and lots of good ideas. And I will be mentioning some of them later. But if you start with that, then you've no idea how this breaks up into simpler component parts. We know that there are simpler parts in nature. We know that we observe three-dimensional space, that we got time, which is something else, and that we got other ideas. How do we get that 10 dimensions breaking down into something else that's simpler? Well, we can't, if that's a starting point. So that kind of thing is okay as a complexity, as an emergent thing, but it's no good as a starting point. So this is not the way we should start. We've got to have something that we can't break down any further, and something like a 10-dimensional space-time with lots of complexity is not something that is fundamental and simple. If there are 10 dimensions, as the string theorists would say, then we should find them by working out how this complexity emerges from something simpler. We shouldn't start with that. And in this, the structures of the components will be diverse in origin, and the brokenness will be because we put them together to make this 10-dimensional structure. That's where we get broken symmetries from. We don't get them at the fundamental level. So we can't just say, there's some concept of symmetry breaking which does this. I don't think there is any such thing as symmetry breaking in that sense. What we have is broken symmetries are certainly a signature of complexity. We put things together, and that's why it looks like a broken symmetry. Not because we had a perfect symmetry and it broke by some mysterious mechanism. We've got to abandon all models. We don't want anything that's model dependent whatsoever. At the fundamental level, models are completely useless. Models are fantastic at most levels of physics, and we need them because complex things are too difficult to do without them. But at the foundational level, then we don't want them. We want pure abstraction. We want absolute minimalism. And abstraction is a good example of minimalism. We want to use Occam's razor as much as we can. The idea that that idea is most likely to be correct, which makes the fewest assumptions. We go for that as much as we can. Not always easy, but that's what we've got to do. We want an abstract reason, everything there just for an abstract reason, and we don't want anything that's complexity driven. What I call the storybook picture. We don't want any of that. We want pure abstraction, we want simplicity, mathematics. Okay, let's go on to the next concept that we need. So let's suppose we've removed everything except physics. So anything that's not physics is out the window. We've removed everything from physics except abstraction. So we can now start from the abstractions. Well, no, we can't. We've got to apply the principle of minimalisms to the abstract ideas themselves. Is nature, if we have a number of abstract ideas, let's say we got space and time and stuff like that, is that good enough? No, it's not going to be good enough. It's not going to be good enough because it's not fundamental enough. Is nature at the foundational level characterized by them? No. Even the abstract concepts, simple as they are too arbitrary to be accepted as fundamental principles. They're not fundamental principles. The only possible statement we could make, and be sure that we would be right, is that nature can't be characterized. It has no defining characteristics. If we want to avoid anything arbitrary, then nature can't have any defining characteristics. We can't say it's all measurable, it's all discrete, it's all continuous, it's all conserved. We can't say anything like that. We can never apply any principle which is true to the whole of nature. It can't be done. Well, is there any principle which can encapsulate this? Well, yes. This is the principle that I believe that we have to accept. This is the metaphysical principle that we have to accept without question if we want to go further. And if we do so, I think we start getting results. This principle says the universe and everything within it, including all the conceptualizing we can do about it, is absolutely nothing whatsoever. The totality is zero. There is nothing which does not have something which causes the zeroing. It's the only position that makes logical sense. It's the only concept that we can imagine that wouldn't be arbitrary if one explained, because it's impossible to explain. Now people say, how is it that we see something around us if the totality is zero? Well, we see something around us because we're in it. If we're in it, then we get a distorted picture of the totality because we can't see the totality. You'd have to be outside it to see it as zero. There's a mathematical example I often use, which is you've got the number 1 and you write that in binary and it's one symbol, the 0 and 1. We know that the minus 1 is needed to cancel it to 0. So 1 and minus 1 are dual concepts, they're symmetric. But if we try to write minus 1 in binary, we realise we've got no symbol for it. And what we do in practical as well as theoretical terms is write an infinite string of 1s. We write an infinite string of 1s. And if we add 1 at one end, you go 1 and 1 is 1, 0, carry 1, 0, 0, 0. You see them all topple down like a set of dominoes. So all the 1s become 0s, so we have an infinite string of 0s if we add 1 to that infinite string of 1s. And so we can do minus 1, and it's of course of practical use in building computers and doing software and so forth. So we can actually do that. But because we've only got one symbol, because we define from within the system, we can't see what it looked like outside. We have no symbol for minus 1. So even though 1 and 1 cancel to 0, they don't look a bit alike. 1 and minus 1 don't look a bit alike, they look completely different. So symmetry there is distorted because of looking at it from one perspective.
Sorry, how do you know the universe is actually like that then?
Well, you have to guess.
Just an assertion.
You don't. Yes, of course I said it's a metaphysical principle. I don't know yet. I've got to guess that it is. You've got to be inductive. You've got to think outside the box. You may be hopelessly wrong. But what I've found is if you are hopelessly wrong, you find out pretty quickly, because everything starts going wrong straight away if you make a wrong assumption. However, if you're on the right lines, then you realise there's one or two little awkward bits, and gradually you look at those and then say, oh no, those awkward bits work out. So you just got to do that. I can only say that to you because I've been through this process. I couldn't say it if I was starting from scratch. But as I'm not starting from scratch, I can say that I found that works for me. Okay. This totality zero, anyway, is not uncommon in the concept is not completely outside of physics as we know it now. It's beginning to creep in anyway. Richard Feynman, for example, pointed out the negative gravitational energy of the Hubble universe effectively cancels out the positive mass energy, and he thought that was quite extraordinary. It costs nothing to create a new particle, since we can create it at the centre of the universe. Well, it will have negative gravitational energy equal to m tot c squared. And this is a great mystery, but he's talking about the total energy in the universe being zero. Cosmologists often talk about starting the universe from nothing. Here we're not only starting from nothing, it's still nothing. But if you start from nothing, you end up with nothing. But you wouldn't know it. You couldn't just guess such a thing. You'd have to have some hunch. Of course, we got hunches. This is science writer Peter Atkins. The seemingly something is elegantly reorganised nothing, and the net content of the universe is nothing. I know Peter Atkins' books are used by the chemistry department quite a lot, so he's a well-known author.
So it finally says that chemistry is nothing.
Yeah, and so is physics, unfortunately. But we needn't tell them that. And even in classical physics, we're very familiar with ideas like the total force in the universe must always be zero. That's what Newton's third law is. And that's what everything that derives from it or is related to it says. Everything's zero, a whole lot. And of course, we're quite familiar with doing that. It doesn't mean that locally we see nothing, we don't. We all see something locally, but totally we see nothing. So the need to make everything total exactly zero would explain why symmetry is so important. It's obvious why symmetry is so important if you need totality zero. That's why we would get symmetry. And in this case, we're looking at a particular kind of symmetry, which is duality. There are other symmetries which we're interested in, but at this moment we're talking about duality. And this provides a clear way of getting totality zero, yet having something happen. And of course, this is another example, conservation of momentum. You start with zero momentum, you end up with zero momentum, but you get two objects flying in opposite directions. Now, I was saying if we want to make it a general principle, we have to realise that it's not going to be obvious how this zeroing happens. It's a subtle foundational zeroing. It's not obviously everything goes to nothing. We can see in some of the examples we've used, like Newton's third law and so on, it doesn't mean nothing happens. Plenty happens, but it's still zero force. So apparent asymmetry or symmetry breaking will come with complexity. And we have to justify this. And we will. We will justify this statement. But I can't justify it today, but I will justify it later, when we look at how complex systems develop from simpler abstract ones. At the moment, let's just accept that this is a principle which we're going to believe applies at the foundational level without exception, without any exception whatsoever. Like physics, it must apply without exception. We've got to find those principles which always apply. And this, we believe, is one. So, we've now got a beginning to get a methodology in place. Foundational ideas have to be simple, symmetrical, mathematically based, minimal, totally abstract, and combined to zero totality. And we have to apply these conditions rigorously, ruthlessly, and in all cases without exception. We've got to get a method that works in every single case. There should be nothing arbitrary whatsoever in the picture. And this is a very important point. If we find such a structure as we can do this with, then it must be totally exclusive. In other words, there must be nothing else other than that. Everything must be within it somehow. And that's a very significant point. If we make things totally exclusive, that adds a very, very powerful constraint to our thinking. So I'm saying we got strict protocols now, and we could make up any protocols we wanted, and if they didn't work, there'd be no use. I want to show in the remaining talks that they do work, that we can actually begin to make headway in this subject, because these protocols do work. But if we didn't have them, I don't think we would make that headway. Now, I want to build up towards the third lecture. The second lecture will be on some mathematics we need. But this lecture here, I want to build up towards the third one. To start looking at how we're going to work on physics. So we want to exclude everything extraneous to reduce the options to the only ones that are compatible with these protocols. And this strictness is absolutely essential as we're reaching the absolute limit of what it is conceivable to know. I think we can actually go to lower levels, but it's no longer recognizable as physics. I'll hope to talk about that in the final lecture. This is only the first step. We haven't established what the protocols will apply to. This is what we've got to do now. What concepts? We've got to look for what we might think the most primitive physical concepts. We've got a fairly good idea, because we've already done this for many years, perhaps even centuries. So we've got a fairly good idea of the kind of things that are the most primitive ones. But we've got to get a strict set of such concepts that we can use. Now, if we go back to our idea that the whole human development of science is only possible because we can recognize repeated patterns, let's go back to the way we have done science up till now, and are still doing it, and still will do it. We go to deeper and deeper levels, and we look for patterns that we've seen before, and we reapply them, and see that they apply there and they don't apply there, and so on. So descending from the large-scale complex structures to increasingly small-scale, less complex ones, it seems that certain concepts are necessary at all levels. Nobody's ever really got away from needing space and time. Others, on the other hand, solidity, materiality, as we've seen, are emergent and disappear. So we obviously don't need them. So it suggests that the repeated concepts are the ones that should appear at most primitive level as well, while the ones which are not repeated we can exclude. If we put forward this kind of analysis, we can create a provisional set of primitive concepts which we can't break down any further, and we've done this in different ways for a long time, but we need to do it in a stricter and more subtle way. The full account will be in the third lecture. However, I want to mention a couple of things at this point. Obviously, we include space and time. I say we don't include space-time, though we will want to get to space-time, because space-time is emergent. If it weren't emergent, we couldn't explain why we got space and time. And space and time in quantum mechanics don't behave the same. We need to combine them in a complex structure, but the fundamental structure needs them separate. And certainly curved space-time is even more emergent. But these emergent properties should emerge from our more primitive ones. We must represent matter in its point-like state, perhaps, and something else, perhaps energy or connection between them. It may be that these aren't the correct concepts, but we find that out by testing it out. We've got to start somewhere, and then as we proceed through, we'll find out which they are. And there must be some way in which at the foundational level these abstract concepts are delivered all at once. So somehow we can't have these as separate things, we must package them, because that is how we get our totality zero, if we package them. And if we package them, that may explain the growth of complexity in the way we do it. So we've got to find out a way of doing that. Now, whatever we find at the first stage won't look like physics immediately, as we know it. Think of it as an embryo type of physics. An embryo doesn't look like a human being, but there are certain indications that a human being is on the way. So this is a kind of embryo, or a cluster of cells perhaps. It won't yet be physics as we know it. But as we unravel the complexity, we ought to see that familiar physics should appear, and with greater clarity than we previously had. And if it doesn't, then we've gone down the wrong track. So we have to see whether it does. Now, people have long thought some great complex equation will hold all of nature's secrets. And as I've said a number of times, nature doesn't work like that. No great complex equation would be anything but arbitrary. We've got to have something that's not arbitrary. The primitive structure has to be mathematical, but it's not an equation. And its secrets will have to be wrung out of it. They won't be obvious. Some of them might become obvious, but many will not. You just have to keep working at them and develop out of the complexity. So this is the primitive embryonic level. I actually tried to invent a German word, and I'm justified in doing that, an Urteil, a sort of pre-theory, if you like. And we need a lot of inductive thinking to do this. We've got to sort of go straight to the X-ray analysis of what we're doing. Go through all the layers of complexity if we can. Maybe we can't, but we've got to try. That's what we've got to aim to do. Because we've got very severe criteria, and we will have an exact mathematical basis, we'll expect it to ensure it's rigorous. And then perhaps we can start answering a few questions which we've never been able to get anywhere near. What are these things? What are things? What are these things? Why is space as we observe it three-dimensional? Why does time never run backwards? Everybody thinks these are deep philosophical questions. I think they're deep primitive physics questions, and we could look at it from that point of view. And if we're getting anywhere near it, then we should be able to start having some idea about how to answer such questions. Okay, let me just point out a few acknowledgements. So this is a long-term research project, and if people want more details, there's the book Zero to Infinity, published by World Scientific 2007. I'm saying that I started off as a solitary worker a long time ago, but I've had several collaborations, and there'll be occasional things in these lectures which I've done with one or other of these collaborators. I will mention it when I have. I also like to mention the support from quite a number of members of Liverpool's physics department, especially from Mike and John, who've been particularly helpful in setting up this series. Yeah, thank you.
And there's actually a symmetry about that third law as well, isn't it? Because you imagine the vectors, and they're images of each other, aren't they?
Well, they are. And the remarkable thing about Newton's third law isn't what people think it is. It's not body A acts on body B acts on body A. Body A acts on the rest of the universe. The rest of the universe acts on body B. And that already is an asymmetry because the body A, the rest of the universe acts back on body A. Body A is localized, whereas the rest of the universe is everywhere. And so already we see, even though it's symmetric in the sense that the total force is zero, it's also asymmetric in another sense.
Yeah, can I ask a question? Isn't it like totally against Gödel's incompleteness law, which is like as mathematical as it can get?
Yeah, but Gödel's laws are based on assuming the number series. 1, 2, 3. We haven't assumed that yet. And I will talk about that in the final lecture, but I can't talk about it today until I've done some other things. Gödel's exclusion law works as we understand mathematics today, but that is based on the already assuming the number series to exist.
So we should invent a new sort of mathematics as well, then?
Possibly, yeah. It's not new in the sense that the mathematics is unlike existing mathematics, but it might explain a little bit more foundational structure in mathematics we should perhaps invent as well. And as I say, physics and mathematics come together. We're not going to have physics separate from the mathematics. It's going to have to come out at the same time. Okay. Okay. Got a few minutes for a few questions. The next lecture will be more mathematical. That will deal with the mathematics we need. And the third lecture is a really key lecture. If you're going to come to any, come to the third and fourth.
You need the second as well.
You need the second as well to understand. And the next lecture will be, as I say, mathematics. We need not special mathematics, but mathematics which may not be familiar. It's not particularly difficult, but it may not be familiar to people, so we need to do it. It's not difficult, though, I can assure you.